Thank you again for the presentation. Today I will address a topic concerning the binder and glaze identification in early Neapolitan paintings. And I will talk a little bit about an imaging system that I developed during my 6 months research at the National Gallery of Art in Washington, D.C. So throughout my PhD, I have been involved in a project of national interest, a joint collaboration among different institutions and laboratories called Sharing Project in the setting of Capodimonte's museum, also partner, of course, of the project. The project was driven by a challenging art historical question that was concerning the introduction of the drying oil as a new binder by Neapolitan workshops during the 15th century and following an already established experience by the Flemish artists. The broader focus of stratigraphies during the transitional period was delved with a multi-analytical campaign on a selected corpus of paintings from the 15th and 16th centuries, ranging from Flemish triptychs to Neapolitan altarpieces or polyptychs, and on a polyptych by Spanish painters, Pedro Fernandez, who was revolving around both artistic circles. As you can see, these paintings were in different conservation state, and today I will present some results from Colantonio's altarpiece because its study benefited from the restoration process. So we had access to the different layers of the painting with more analytical means. Okay. So let's start with the attempt to map binders, which is actually a very challenging topic for this altarpiece with hyperspectral imaging at the middle stage of the varnish removal in the SWIR region. This region is particularly interesting because there's the occurrence of combination bands of amides and methylens, so lipidic components that can be shared both by drying oils and tempera. And this region allowed to map extracted end members, so spectra representing purest pixel in the spectral cube. One end member here is related to animal glue that was found in a part that we know for sure it was restored. So we're not really interested in that. The two other components are, one is a lipidic component, let's say, and the other one is a lipidic component broadened by the varnish. As you can see, it is mapping in the same, the orange component is mapping in the same region as the varnish that is showed in the ultraviolet induced fluorescence image. We did not find any evidence of amide features implying the presence of a proteinaceous binder, even though historians of art and restorers believe there were areas of the painting on the draperies of the monks where they could spot a different behavior of the paint. So to delve a little bit more into this question, we used a combined approach involving Fourier transform infrared spectroscopy in external mode to characterize the surface of two areas of the drapery, one on a lighter part and one on a shadow, and micro FTIR in attenuated total reflection mode on a cross section taken from a lighter shade of the drapery that gave information about the inner layers. So non-invasive FTIR showed in the blue spectra amide bands in the lighter shade, cross-checked then with the stratigraphic analysis provided by the sample. So at the interface of the ground layer and the first pictorial layer, we could map the coexistence of lead carboxylates and amide 1 feature that could be related to a proteinaceous binder. Since we know that lead soaps are a degradation product that is usually associated with drying oils, we suggested that a presence of tempera could be found maybe under a layer of drying oil, or there could be an emulsion. Provided also that previous work showed that in the presence of tempera, actually there is like a faster production of metal soaps. Focusing on the characterization of glazes by combining elemental mapping through macro XRF, molecular mapping through hyperspectral imaging in emission mode, and FTIR spectroscopy. We investigated both the distribution and the binding media of the glaze in the shadows of this drapery of the angel, while potassium map is giving an indirect marker of a possible presence of an organic lake, then hyperspectral imaging is actually mapping the contribution of this possible anthracynonic red lake, giving a good comparison with the emission of a glaze of Madder Lake in oil, covering an underlayer of cinnabar in oil. And this is a mock-up that we purposely prepared. FTIR, on the other side, is indicating an oil-raising binder for the glazing, and this part of this point is also showing an oxalate patina. So these results raise important methodological question. Would we have been able to fully characterize binders and glazing material without taking samples? Can we fully replace a sampling with non-invasive approach? And if so, to what extent can we be reliable about binders, especially in the presence of surface glazes or varnish? In order to try to answer these questions, we designed some mock-ups, of course. So from the diagnostic findings and the optoptic observation, and alongside art historians and restorers, several questions regarding painting technique were formulated, leading to the design of mock-ups. And the choice of pigments, binders, and layering was informed by historical recipes and treatises that were coeval to the historical period and production of the painting. Different imaging techniques, of course, were performed on these mock-ups, and for the purpose of this presentation, I will focus just on results from the hyperspectral imaging in the SWIR region that was acquired with a push-broom scanner from Clyde. So the processing of this hyperspectral cube on the mock-up glazes with a specific pipeline that I implemented with John Delaney from the National Gallery allowed me to extract relevant features for binder mapping in two regions that are quite informative in this sense. The first one I'm showing in this slide is the one related to the combination bands of amide that we saw also earlier. As you can see, different end members related to proteinaceous binder of the paint were extracted in this region alongside a feature from azurite. And it was possible, for example, as seen in the mapping on the left, to distinguish cinnabar in egg yolk from the one in linseed oil, as well as azurite in egg yolk or in animal glue. In real cases, it is much more difficult to spot this feature from egg yolk and animal glue that are quite close in the spectra in terms of like position of the features, and they have also a tiny contribution. But we can aid the interpretation of this region with the one I am showing next, which is another informative region where I employed the same data processing pipeline, and it's related to the combination bands of methylens, carbonates, and hydroxyls group. In this case, it was possible to separate better animal glue and egg yolk binder for the presence of lipidic contribution in egg yolk that is absent in animal glue. And it was possible to differentiate the lipidic contribution of egg yolk and drying oils in underlayers of cinnabar. What becomes difficult is characterizing the glazes on top that are thin layers. So while SWIR spectroscopy was quite affecting to probe the subsurface feature through the glazing layers, it is more sensitive to the optical response of the bulk material. So we are relying on overtone and combination bands. We are not that specific in terms of like chemical features. So if we are interested in the surface materials and in the glazing layers, we must provide a spectral region that is more sensitive to the surface layers, basically by broadening the spectral range and delving into the mid-IR that has more chemical specificity, and it's characterized by the fundamental vibrational absorption. That's why in the last 15 years, a lot of effort was spent on developing imaging equipments in the Mid-SWIR region. They provide higher sensitivity to the surface while also having higher spectral resolution due to the interferometric approach. So this is a broad overview of all the systems that were developed in this last 15 years. And they can broadly be classified in 3 acquisition architectures: point scanning, push broom systems, and full field imagers. None of this system is simultaneously maximizing all the characteristics that I've listed above, as you can see, but each one is representing a compromise. So point scanning systems excel at providing high quality spectra in a broad spectral range at the expense of a slower acquisition time that is actually very time consuming if we have to acquire a cube on a large painting. Push broom systems are much faster and can cover large paintings, but the spectral range can be usually a little bit narrower, so we're not that sensitive to certain features. Full field imagers prioritize faster acquisition rates and good spatial sampling at the expense of a lower signal to noise ratio, and also they employ very expensive focal plane array detectors and complex optical systems, so they need a certain expertise to be handled. So building on these premises and with the aim of providing a more affordable system with good performances, at the Chemical Imaging Lab of the National Gallery, we developed this prototype based on an Coptics spectrometer. Comparatively to the previous system that were point scanning, that were employing a thermal detector, the only difference is that this spectrometer, it's using a quantum detector, an MCT, that is cooled with a liquid nitrogen. So this detector is the main advantage of the system because it allows a faster acquisition and with also providing high performances on the spectral quality. The spectrometer, so it's in a stable free running configuration while the artwork is scanned on a motorized easel. And at the same time, we have the synchronization of the acquisition of the spectra and the motion of the easel made by a microcontroller and Arduino board. To be more clear, what happens is that while the motorized easel is moving, it sends a 5 Hz TTL pulse to the microcontroller board that is interpreting this position trigger, and it's sending a key to the laptop where MATLAB is running. MATLAB is basically dealing with all of this process of receiving the trigger and starting a TCP/IP connection with the spectrometer that is basically run by an interface called EODAC. This interface is acquiring the interferogram and retrieving the spectra to MATLAB that then stores the spectra in a single row. So at the end of the acquisition, we will have a sequential spectra in a single row in a single binary file. So we will have the same number of binary files as the number of the rows of our acquisition, of our cube. My coworker from the Chemical Imaging Lab, Amar Rizbud, was heavily involved in the custom processing routines in MATLAB to deal with the acquisition of the dark and baseline spectra, the acquisition of the row cube, and then the unpacking of the cube. This means going from a binary file to an MV-compatible dataset, because you usually use MV to process then the data. And after obtaining cubes for dark and baseline of the same size as the row cube, we can flat fill this cube and then calculate the sealed absorbance, which is the quantity that we need for subsequent analysis. So at this point, where does our system stand in comparison with the previously developed one? It provides a spectral coverage that is sufficient for our purposes. A competitive spatial sampling, because it's 1 millimeter of step, but most importantly, a scan rate of 1 or 2 order of magnitude faster than the previously developed system that employ a thermal detector. So it is competitive with also imaging systems if we look at spectral quality, signal to noise ratio, and affordability. It's much less expensive than an FPA. The following results that I will show you were obtained on this mockup that is like 29 by 21 square centimeters of area, acquired, as you can see, in a little above 3 hours long acquisition. So FTIR hyperspectral cubes were converted to absorbance and then processed using the same data processing that I showed you before on the SWIR cubes. I am showing here the broad range divided in the SWIR and Mid-IR region only for purpose of visualization of the M members extracted with their distribution on the map on the left. In this case, I am showing a paint of indigo bound in animal glue, partly covered by a varnished base glaze of Buckthorn Lake, glaze represented by the red spectra. And what we can see is that in the SWIR region, we don't really have a big contribution from the glaze, if not with a slight broadening of the combination bands of the lipid of the varnish. Whereas in the Mid-IR region, the glaze is hindering features from both the indigo and the binder. Another case that is actually very interesting is the one of cinnabar, where I'm showing the comparison among cinnabar bound in egg and two different glazes with the same pigment, a Kermes lake, but in one case bound with linseed oil, in the other with a varnish. The interesting aspect of this comparison appears in the Mid-IR region, where we can see a different behavior in hindering the contribution from egg features of the underlying paint, highlighting also the possibility to separate an oil-based glaze from a varnish-based glaze. Last example shows azurite bound in egg, a mixture of azurite and lead tin yellow bound in egg, and this paint partly covered by a varnish-based verdigris glaze. The interesting aspect here is that I'm showing a pigment that displays absorption both in the SWIR and in the Mid-IR region, so it's actually very difficult sometimes to understand the binder of azurite. And it's interesting to see how mixing azurite with lead tin yellow, in this case, that has no specific absorption in this region, shows more characteristic features coming from the binder, because the ratio pigment binder is lower. The glazing on top is quite interesting just in the SWIR region, because it is the only case where we actually see a glaze in this range, impacting this range, not because of the binder, but because of copper acetate absorption features coming from the pigment. So to conclude, what we understood from this work was that non-invasive hyperspectral imaging in the SWIR is not sufficient to describe binders and glazing on a stratigraphy, and it's much more powerful to aid the interpretation by broadening the spectral range, employing, of course, a mapping approach. What could be interesting as a perspective could be to design maybe a neural network that can perform data fusion on this mid-SWIR imaging data and the SWIR data obtained maybe with a dispersive system that has higher spatial resolution, so that we can obtain maybe chemically informed maps at a higher spatial resolution. Some references, and then I want to thank, of course, the group that was involved with me in this project, and thank you all for the attention.